Hello everyone, welcome you back to another video. In this video we are going to discuss about two remaining asymptotic notations, right? So in the previous classes we have discussed three asymptotic notations. One is big O, another is omega, and third one is theta. So today we are going to discuss about two things. One is small o and second one is little omega. Okay, so these two things today we are going to discuss. Read the definition of small o. Fn equals to small o of g of n if for all c greater than 0 f of n less than c into g of n for all n greater than equals to n naught. So in the big O definition I have said that f of n equals to big O of g of n. This is the big O and this is the small o. Okay, so big O of g of n if fn less than equals to g of n, c into g of n. So here is the actually difference. Fn is less than c into g of n, and here fn is less than equals to c into g of n. Gn must be strictly greater than f of n. So this is the difference between small o and big O. Other things are same. So if you haven't seen my Go notation, then you can go and watch the previous videos. Same goes for little omega. So in the big omega, what we have read that f of n must be greater than equals to c into g of n, right? But in little omega, f of n will be strictly greater than g of n. So this is the difference between big omega and little omega. Nothing much to read about them. Everything will be same as big O and big omega, but the difference is it is strictly c into gn is strictly greater than the f of n, and here f of n must be strictly greater than c into g of n. So this is the difference you need to know. Let's see some of the properties of asymptotic notations. Okay, to understand these things clearly, you need to have some prerequisite knowledge about relations. You can read it in discrete mathematics, but I will be giving a brief idea about what is transitiveness, what is reflexivity, what is symmetricness. So what is transitive? Transitive means, suppose this is a person. Okay, this is another person, this is the third person. This one is related to this one. Suppose it is A, this is B, and this is C. Suppose A is related to B, B is related to C. That means A is also related to C. Okay, I'll be taking a relation and showing you what is this implies. Suppose the relation is taller. A is taller than B. A is related to B means A is taller than B. And again, B is related to C means B is taller than C. Then obviously from these two statements we can derive that A is taller than C. So if this thing satisfies, these two are given to us, and this is the third thing we have to derive from these two statements. If we can derive this from these two statements, then we can say that the relation which we are taking is a transitive relation. Okay, so this is the brief idea about transitiveness. So let's see which asymptotic notations are following which properties. Okay, so for big O definition is f of x equal to big O of g of x if f is less than equals to g of x. This is the definition actually, so I am writing this in shorthand. F is less than g because f of x equal to big O of g of x, and then g of x equal to big O of h of x. Suppose then g will be less than h. Okay, according to the previous videos you can see that how big O will work. If you don't see, please go back and watch the big O videos and then come back to here. From this we can say that f is less than equals to h. That means I have f of x equal to big O of g of x, and I have g of x equal to big O of h of x. What this implies? This implies f of x is less than equals to g of x. This implies g of x is less than equals to h of x. So our relation is big O. So can I write f of x equals to big O of h of x? What does this mean? This means f of x is less than equals to h of x. Can I derive this from these two? Yeah, definitely I can derive it. So big O follows transitive property. So I think you must have cleared about this transitiveness of big O. Now let's come to big omega. Okay, so how I have proved this one? According to this, you can prove this also, because f of x equals to big omega of g of x. What does this mean? This means f of x is greater than g of x. Which one is at this position? That must be greater than the function that is inside the big omega, right? So if this is true and g of x equals to big omega of h of x, then that means g of x is greater than equals to h of x. What I have written here, right? Then obviously f of x will be greater than equals to h of x. So big omega also follows the transitive property. For theta showing if two functions are asymptotically equal, then we are using the theta notations, right? So here f equals to g equals to h, then obviously g equals to f equals to h, that will be also true. So theta also follows the transitive property. About the small o, f is strictly less than g is strictly less than h, then obviously f will be strictly less than h. You can take an example: f is a person, g is a person, h is a person. Taller, whatever we have taken in the previous example, g is taller than f, h is taller than g, and definitely h will be taller than f. So small o also follows the transitive property. Small omega also will be following the same property. You can apply the same logic to it and can get the proof done. Then come to reflexivity. What is reflexivity? Reflexivity means if a entity is related to himself, then we can say that relation is reflexive in nature. Here it is big O. Big O is here. Big O means f of n equals to big O of f of n. Can I write it? Because big O is the function I am using. Can f of n, I can write it as f of n equals to big O of f of n. Yeah, absolutely I can write it as, because the definition of big O is f of n, this term must be less than equals to this term. So f of n must be less than equals to f of n. As here less than equals to is present, so this can be true. Same goes for big omega, because that will be greater than equals to. So this is the equals to that makes this big O and big omega reflexive in nature. But if you use the same thing for small o or small omega, so that can't be true for their case, because that is strictly increasing or strictly decreasing, right? Either f of x must be less than g of x, or f of x must be greater than g of x, but there is no thing of equal to, so that makes them incompatible for reflexive nature. Now come for theta. So theta we represent those asymptotically equal functions, so I can definitely say as f of n equals to theta of f of n, so there is no problem. Next, coming to symmetric property. First, what is symmetric property? Symmetric property means if a entity A is related to B, then B should be related to A. This is given and we have to derive this. If something A is related to B, then B should be related to A. So suppose I am taking the big O. I am saying that f of n equals to big O of g of n. That means f of n must be less than equals to g of n, right? Can I write it as g of n equals to big O of f of n? Absolutely not, because this statement means g of n is less than equals to c into f of n. These two are contradictory in nature. The same applies for big omega, small o, and small omega. So all those four will not compatible for symmetric property, but only theta will be compatible, because I can write it as f of n. If I can write f of n equals to theta of g of n, then I can derive from this g of n equals to theta of f of n, because they are both asymptotically equal. Only theta will follow the symmetric property, other two will not follow the symmetric property. So that's all for today. Thank you for watching the video.